Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends, in this video we will study about the measurement of vibrations. We will start that why the measurement of vibrations is necessary, what is the nature of the vibration, which instrument is used for the measurement of vibrations, and what are the types of these instruments, their advantages, disadvantages and applications. So let us start with the topic. Whenever any instrument or device is used for measurement purpose, then the first and the foremost requirement which is expected from the instrument or device is that it should be susceptible to the environmental conditions. If there is any change in the environmental conditions, then those conditions will not affect the measurement or the readings of the instrument. Okay, so the instrument, it should be less affected by the environmental conditions, and in those environmental conditions, one of the condition is the vibrations. So the measurement of vibration, it becomes very important for the measurement purpose, because the instruments and devices, they should not be affected by the vibrations or shock in the surrounding environment. So this measurement of vibrations is very important for the instruments and devices or the equipments used for the measurement purpose in the laboratories and in the research applications. So as I have said that the vibrations measurement, it is very important for the instruments and equipments. So whenever when the instruments are manufactured, then on those instruments specifications are written, and one of the specification is about the vibration that the instrument can withstand. So the maximum amount of vibration levels that can be withstand by the, or that can be tolerated by the instrument or the equipment, they are specified on the instrument while they are manufacturing. Okay, now the vibration measurements, they are carried out on rotating and reciprocating machinery, because in the rotating and reciprocating machineries, continuous rotations of the equipment is being done. The various parts of the machinery, they are rotating continuously, so due to that rotations, vibrations are produced. So vibration measurements are carried out on the rotating and reciprocating machinery for the analysis, design and for the troubleshooting purposes. Now the example of these rotating and reciprocating machineries is the power station, turbines and generators. So in turbines and generators, the machinery is rotating, so due to that vibrations are produced. So vibration measurement is done in these machineries. Now whenever we say vibration, then what does this vibration means? Suppose that an object, it is put on a table. Okay, this is the top of the table, and on that an object is being placed. Now if we say that this object is vibrating over the table, what does that mean? It means that this object is initially at the rest position, and this is the mean position or the center of the object. Now around this center position, this object is displacing itself, or it is moving around its mean position. So vibration means that the object is displacing in the forward and the backward direction around its mean position. So vibration is nothing, we can say that it is the displacement of the object around its mean position. Okay. Now this is the vibration. Now what is the nature of the vibrations? Most of the vibrations, they are the sinusoidal displacement. So if we talk about the nature of the vibrations, most of the vibrations are sinusoidal in their nature. And as I've said that vibration is the displacement of the object around its mean position. So we can say that this displacement is sinusoidal displacement. So because the vibrations are sinusoidal in their nature, so we can define the vibrations in terms of its amplitude and in terms of its frequency. So when we define the sinusoidal the vibration in terms of amplitude and frequency, it is given by the relationship x is equals to xm sine omega t, where xm is the amplitude and omega is the frequency. This frequency is the angular frequency, so it is defined, its unit is radians per second, and xm is the amplitude and x is the displacement. So we can say that vibration, which is nothing but a type of displacement, this displacement is a sinusoidal displacement, and this displacement can be defined in terms of its amplitude and frequency as x is equals to xm sine omega t. Now this is displacement. If we want to find out the velocity, then velocity is the differentiation of the displacement, that is x dot. So if we differentiate this, we will get x m omega sine omega t, because velocity is equals to dx by dt, differentiation of displacement with respect to time. So here if we differentiate this, we will get xm omega sine omega t, which is the velocity. In that, if we find out the maximum velocity, then maximum velocity v naught is equals to xm omega. So we can write this velocity as v naught sine omega t. Now if we want to find out the acceleration, then acceleration is given as the differentiation of the velocity. So acceleration is dv by dt, or we can say it is d2x by dt square, that is double differentiation of displacement, and dv by dt, that is differentiation of velocity. So if we differentiate it, we will get minus of xm omega square sine omega t. We are differentiating this term, or we can say we are double differentiating the displacement. Now here, if we found out the maximum acceleration, so A naught is equals to minus of xm omega square. So this was the amplitude, this is the maximum velocity, and this is the maximum acceleration. So from this equation and this explanation, we can conclude that any type of sinusoidal variation, it can be measured by measuring the amplitude, velocity and acceleration and frequency of that vibration. If we have calculated these variables, these parameters, displacement, acceleration, velocity and frequency, we will be able to measure the vibrations. So all the types of vibration measurements, they are concerned with the measurement of these quantities. Okay. So vibration measurement is concerned with the measurement of the four quantities: displacement, velocity, acceleration and frequency. So the peak values of these quantities should be measured. Okay. And we know that displacement, velocity and acceleration, they are correlated with each other. If we are having the value for displacement, we can easily measure velocity and acceleration by differentiating it. And if we know the value for acceleration, we can find out velocity and displacement by integrating its values. So if out of these three variables, if any one of the variable is known to us, then we can find out the other variables with the help of differentiation and integration by using the electronic devices. Okay. Now here, as I have said that the vibration measurements, they are concerned with the measurement of these four quantities. So it can be done with the help of using a transducer which is sensitive to the displacement, velocity and acceleration. So any of the transducer which measures displacement, velocity and acceleration, that can be used for the measurement of vibrations. So this transducer is going to give us the output signal, okay, according to the displacement, velocity and acceleration, and the output of this transducer is then fetched to the display device, which is going to give us the readings of either the displacement, velocity or acceleration or any other quantity which depends on it. Okay. So transducer is going to provide us an output. This output is fetched to the display device, which give us the readings. So readings are either for the displacement, velocity and acceleration, and we can find out the other variables depending upon their relationship with it. Okay. Now this was about that how the vibrations are measured, and we have seen that vibrations are measured by using a transducer which is sensitive to the displacement, which can be the amplitude, we can also say, and velocity and acceleration. So the transducers which are used for the measurement of vibrations, they are called the seismic transducers. So these transducers, that is seismic transducer, they are also called the seismic accelerometers. accelerometers because they measure the acceleration. So these transducers, they are going to measure the amplitude, or we can say the displacement, velocity and acceleration. And with the help of these quantities and frequency also. And by measuring these quantities, we will be able to find out the measurement of vibrations or the magnitude of the vibrations applied to the device. Now let us first see the construction of these seismic transducer. First we will see its diagram. So this is the diagram for the seismic transducers, or we can say the seismic accelerometers. You can see that it consists of a mass, damper and spring arrangement is there. Damper is connected, which is having the value B. Then a seismic mass M is connected. Then we have the spring having the spring constant K. Now to this seismic mass, the displacement transducer is connected, and this seismic transducer or this arrangement is kept over the workpiece on which the vibrations are being applied. Now when the vibrations are acting on this workpiece, or we can say that the instrument or device on which the vibrations are acting, so due to those vibrations, this transducer, this arrangement of the seismic mass, spring and damper, that is also going to vibrate. Okay, and this mass, it has the ability to get to come to its rest position when it is vibrated. Okay, so when vibrations are applied to this workpiece, so due to those vibrations, spring, mass and damper arrangement, that is also going to move. Okay, and movement means displacement has been caused. So displacement of this seismic mass is measured by the displacement transducer, and this displacement is proportional to the magnitude of the vibrations. Okay, so we have measured the displacement or amplitude. So with the help of that, we will be able to find out the velocity, acceleration and the frequency. So this was the construction. If we see the main parts of the seismic transducer, then we are having a mass which is connected through a parallel spring and damper arrangement. And this whole arrangement of mass, spring and damper, it is kept in a housing. So this is the housing, or we can say frame is there. So this mass, spring and damper arrangement along with the housing is kept on the workpiece, whose vibrations we want to measure. Now due to these vibrations, this mass and the damper and spring arrangement, that is also going to be displaced in its position. And this displacement or movement of the mass with respect to the housing. In the diagram you can see that when vibrations are being transferred to the seismic mass, that is also going to displaced. So this displacement of the seismic mass and the housing with respect to this housing, that motion is being measured by the displacement transducers. Now these seismic transducers, they can operate in two different modes. One is the displacement mode and second is the acceleration mode. So in two modes, the seismic transducers can be used. The difference between the two modes is the type of spring and mass used for the measurement. In the displacement mode, a large mass and a soft spring is used, whereas in the acceleration mode, a small mass and a stiff spring is used. So for the displacement mode, we will be having large mass plus soft spring. Whereas in acceleration mode, there will be small mass plus stiff spring. So that is the difference between the two modes. Now if we see the diagram for the seismic transducer, we will see that we are having a damper, mass and spring which are connected in a parallel combination. So if we draw the mechanical system for this seismic transducer, then that mechanical system can be represented as, we are having a damper, then spring and mass are connected, and these are the two nodes x1 and x2. Okay, x1 is the xm cos of omega 1t. The value of x1 is given xm1 cos omega 1t because we know that the vibrations are always in the form of a sinusoidal vibrations are there. So we have represented in the form of xm1 cos omega 1t, and x2 is the displacement of this seismic mass. So x2 is here, this is x1, the two nodes, spring, mass and damper arrangement. Now if we write the equation of motion for this arrangement, then it can be written as, we know that x1 is equal to xm1 cos omega 1t. This is our input, that is the vibrations. Equation of motion is represented as m x2 dot plus b x x2 dot m x2 double dot plus b x2 dot plus k x2, because b, m and k both are both these three are related with the x2, and on the input side we are having only this damper b x1 dot plus k x1. Mass is not connected with it. So this is the equation of motion for this. Now Here our motive is to find out the difference between the x2 and the x1. We want to find out x2 minus x1. So what we will do, we want to find out this difference. So we are going to divide this whole equation by m. Now we want x2 minus x1. So x2 minus x1 will be, x2 term is here, x1 term is here. So we will bring these two terms on this side and the remaining terms on the right hand side. So x2 minus x1 is given as exponential So this is x2 minus x1, that is exponential of this term, whole term is there, and this additional term. So this term is called the transient term, and this term is called the steady state term. Okay, so transient term and steady state term we have got, and this is the difference between the two displacement. X1 was the input and x2 was the output. Now if we find the frequency omega d is given as k by m minus b by 2m square half radians per second. Now if we suppose that only the steady state term is there, all the transient part in the vibration has died out, all the transients has died out, only steady state term is there. So using this steady state term, if we find out its amplitude or the displacement, then the steady state term was, so if we write the steady state term, so steady state term is given as m xm1 omega 1 square cos of omega 1 t plus phi. Phi is the phase angle, and here we are having k minus m omega 1 square plus b square omega 1 square and half. Now this is the complete steady state term. Now in this term, if we see the amplitude, then amplitude will consist of this part. So this is the amplitude of the steady state term. We can write it as x2 minus x1 m, because when we have written x1, so x1 was xm1 cos of omega 1 t, and xm1 was the amplitude. And here, because x2 minus x1 is this complete term and we are taking only the amplitude part, so we have added the subscript m here, and this is m xm1 omega 1 square upon okay. Now dividing this complete term by m. So when we divide this, here we will get k by m. This m will be cancelled. M here it will be cancelled. Here we will get b by m whole square, omega 1 square and half. So dividing this complete term with m, that is capital M mass. So we will get xm1 omega 1 square. This is k by m minus omega 1 square plus b by m square omega 1 square and half. Now why we have divided this by m? Because the natural frequency is given by omega n, which is under root of k by m radians per second. And if we talk about damping ratio, then damping ratio del is given by b by 2 under root of k m. So in this equation, if we write this amplitude in terms of the natural frequency and the damping ratio, then this can be modified and written in the form x2 minus x1, the amplitude, xm1 okay. So all the terms there, because we have replaced this the natural frequency, and in the terms of del we have modified this amplitude. Now this ratio omega 1 upon omega n, that is the frequency, actual frequency divided by the natural frequency, is called the normalized frequency, and it is represented as u and given by the ratio omega 1 upon omega n. So all these ratios, they will be replaced by this normalized frequency. So x2 minus x1 m is equals to xm1 u square upon 1 minus u square whole square plus 2 del u square and 1 by 2. So we have written the displacement or the amplitude in terms of the frequency. Now here we can see that as the frequency is increasing, the amplitude difference is also increasing. And as we have measured, we have the value for the frequency also, we have the value for displacement. With the help of displacement, we can find out the velocity and the acceleration. This was the amplitude, or we can say the displacement. By differentiating it, we can calculate velocity and the acceleration. So the output of the seismic transducer is an indication of the acceleration of the vibrations, or we can say the amplitude or the displacement. Okay, and vibrations, they are measured in terms of these four quantities, so we have measured it. So because the output is an acceleration, that is why it is called a seismic accelerometer. Okay, because output of this transducer is an indication of the acceleration of the vibrations. Now in this seismic transducer, when we have seen its construction, we saw that to the mass, damper and the spring arrangement, to the mass we have connected a displacement transducer, and the function of this displacement transducer is to measure the displacement caused in the mass. Now depending upon the type of displacement transducer used, there are various types of accelerometers. Like if we have used the potentiometer, then it is called the potentiometric accelerometer. If we have used Lvdt as the displacement transducer, then it is called Lvdt accelerometer. If we have used the piezoelectric crystal as the displacement transducer, then that is called the piezoelectric accelerometer. So depending upon the type or the displacement transducer which we have used, there are different types of seismic accelerometers. So here we will study the three types of accelerometer: piezoelectric, potentiometric and Lvdt accelerometer. First, we will start with the potentiometric. The working principle remains the same in the accelerometers. It will also, all the accelerometers will have the mass, damper and the spring arrangement, and to the mass the displacement transducer is connected. Here the displacement transducer is a potentiometer, and we know that in the potentiometer it works on the principle that due to the change in the resistance, an output voltage is generated. Okay, so the movement of the wiper of the potential of this potentiometer is going to change the resistance, and due to the change in resistance there will be a change in the output voltage. Okay, so let's see first the diagram for this potentiometric accelerometer. So this is the diagram for the potentiometric accelerometer. Here you can see that again we are having the mass, damper and the spring arrangement. Okay, damper is here damping is provided by either filling this box with the heavy viscous fluid or by using a dashpot. Now to this mass, because we have to connect the displacement transducer to it, so here the displacement transducer is the potentiometer. In potentiometer we are having a resistance, and on this resistance the wiper or the sliding contact is moving. So wiper is connected with this seismic mass. Okay, now when vibrations are provided to this accelerometer, okay, so due to those x1t, that is the input vibrations, the displacement in this seismic mass is produced. So this displacement is x2t, okay, and input displacement is x1t. We have already derived the relationship between x2 minus x1, that is amplitude. Okay, now when this mass is going to move, this wiper is also going to move over this resistance. Okay, and due to that there will be a change in the resistance. Okay, so either we can directly measure the change in the resistance, or if we are using this potentiometer as a potential divider, then we can find out the change in the potential also. Okay, so both change in resistance or we can say the change in the potential is proportional to the vibrations which are caused. Okay, so in this way the potentiometric accelerometers, they measure the variations by measuring the change in resistance or the change in potential by using a potentiometer. So this was the construction and the working of the potentiometric accelerometer. If we talk about its disadvantages, so this limited resolution is provided. Generally, the resolution is good at very low frequencies. So due to this disadvantage, the applications of this potentiometric accelerometer, it is limited to very low frequency ranges. Lower than 50 Hertz. So this type of potentiometric accelerometer, it is useful for the low frequency applications only, and its disadvantages are that it is having very limited resolution and errors can also occur due to the presence of the sliding contact. So this was potentiometric accelerometer using potentiometer as the displacement transducer. Next is the Lvdt accelerometer. In Lvdt accelerometer, the displacement transducer is Lvdt. The full form of Lvdt is linear variable differential transformer. It is also a displacement transducer. So here the displacement is converted into an output voltage. Lvdt measures the changes in the displacement by measuring the change in the output voltage. Okay, so let's see its diagram. So this is the arrangement for the Lvdt accelerometer. In this you can see this much part is the Lvdt. In Lvdt there are one primary winding and two secondary windings. In between the primary and the secondary windings there is a core. So that is why it is called linear variable differential transformer. Okay, because it is having the primary and the secondary windings in it. Now as this core is going to move, so due to that the potential, the voltage which is linked with these two secondary windings, that is also going to change. And here we are measuring the difference in the potential generated. So it is a differential transformer. So the output voltage is the difference in the voltage which is induced in these two secondary windings. So it is a differential. T is the transformer. Okay, so this is the primary winding and these are the two secondary windings, that is S1 and this is S2. Now when this core is in just in the middle, the difference, the EMF which is induced in these two secondary windings will be equal. So output voltage will be 0 because we are calculating the difference ES1 minus ES2. Now, if this core is being displaced, so EMF induced in these two secondary windings will be different, and we will get some value for this ES1 minus ES2. There will be some particular value. So that difference in the output voltage is a measure of the displacement of this core, and this displacement is due to the vibrations caused in this workpiece. Okay, so this is our input vibration, that is x1t, that is input displacement is there, and this input displacement is causing the displacement of the core. Core is connected with rods. There are two reeds. Okay, so the core is connected with this housing with the help of these two reeds and the rods. Okay, so this vibration is being transferred to the core and it will be displaced. According to that, output voltage will be changed. Okay, and in this way the LVDT is acting as the displacement transducer here. So, as we have seen in the seismic accelerometers that we were using the mass, damper and the spring arrangement. So here the core of the LVDT is acting as the mass, and to the mass the in output, that is x2t, the displacement is being caused. So core of LVDT is the mass, and this core is attached to the rods, and there are two rods, so these rods are acting as the spring, and we are having to the two rods the two reeds are connected, and to these reeds the vibrations are being provided. So just that seismic transducer arrangement, that is mass, damper and spring arrangement, it has been converted here. Core is acting as the mass, rod is acting as the spring, and vibrations are provided to the reed. Okay. And the magnitude of the differential output voltage produced, that is an indication of the vibrations which are given as the input. So this was the construction and working of the Lvdt accelerometer. Now comes its advantages. Now Lvdt, it offers very small resistance to the movement. Than the potentiometric type. So due to this low resistance, it is going to provide us a better resolution. In potentiometric type, we have studied that it is having very limited resolution, but that problem is being reduced in the LVDT. In LVDT, it has very low resistance to the motion. So due to that, it can provide better resolution. Also, it is a contactless device. So due to no contact, the problems due to friction is being reduced. The LVDT, it has very much smaller mass, so due to the small mass it will have high natural frequency. So this LVDT, it can be used for the higher frequency applications, which was a limitation in the case of potentiometric type. So these are the advantages of the Lvdt accelerometer. If we talk about its application, then they are used for steady state, so this was the construction, working, advantages and application of the Lvdt accelerometer. Now the third type of accelerometer is the piezoelectric accelerometer, which uses the piezoelectric crystal as the displacement transducer. We know that in the piezoelectric crystals, when they uses the piezoelectric effect, that when the piezoelectric crystal is compressed or a force is applied on it, then an output voltage is generated. So first we will see its diagram, its construction, then we will see its working. So this is the arrangement for the piezoelectric accelerometer. Here you can see this is the piezoelectric crystal. This is the seismic mass. Okay, so here the vibrations are provided, that is x1t, and due to this the displacement of the seismic mass occurs, that is x2t. Here we have a clip type spring. So just in the accelerometer transducers where we were having the mass and the spring arrangement, here also we are having mass and the spring arrangement. Now this mass is kept over the piezoelectric crystal. So due to these vibrations, the seismic mass is going to produce the displacement. There will be a displacement in this, and due to that a force will be applied on the piezoelectric crystal. Due to this force, this piezoelectric crystal is going to get deformed and an output voltage is generated. And this output voltage is proportional to the force applied, which is proportional to the vibrations. So in this way, if we measure this output voltage, that will be an indication of the vibrations. So input vibrations, they are going to cause the displacement of the seismic mass. This seismic mass is going to apply the force on the crystal, and due to that force on the crystal, it is going to get deformed, because the piezoelectric crystals, they work on the piezoelectric effect, and that piezoelectric effect says that when a force is applied on a piezoelectric crystal, then an output voltage is generated. So due to this deformation of the crystal, an output voltage is generated. So we can say that this output voltage is proportional to the input vibrations. Okay. So in this way, the voltage generated across the crystal will give us an indication of the input vibrations. So this was the working of the piezoelectric accelerometers. Now comes its advantages and disadvantages. The first advantage is that this instrument is very small in size, so it will have very small mass. It has a small weight. Also, its natural frequency is very high. So because its natural frequency is very high, so it can be used for the high frequency applications. So these are the advantages of this piezoelectric accelerometer. Now here the piezoelectric crystal is being used, and this piezoelectric crystal is having very high output impedance. And due to this high output impedance, there will be problem of loading effects. So to remove this problem of loading effects, the monitoring system should be used, which is going to have a very high input impedance, so that this loading effect will be reduced. So that is one problem occurring in the piezoelectric accelerometers, that crystal is a source of very high output impedance, and high output impedance means that loading effects are there. So to reduce the loading effects, we have to use a system which is having very high input impedance. Also, as I've said, that this type of accelerometer is useful for high frequencies, because at low frequency its response is very poor. So because at low frequency its response is poor, so this type of piezoelectric accelerometer should not be used where the frequency is very lower than 10 kilohertz, 10 hertz. Okay, so if the frequency is lower than that, so for such lower frequencies the piezoelectric accelerometers cannot be used, because at lower frequency its response is very poor. So these are the advantages and disadvantages of this. We saw its applications also, that it is used for the high frequency applications where the vibrations are having very high frequency. So these are the three types of accelerometers depending upon the displacement transducers used in them. If potentiometer is used, then potentiometric accelerometer. If Lvdt is used, then Lvdt accelerometer. And if piezoelectric crystal is used as displacement transducer, then it is the piezoelectric accelerometer. All these accelerometers, they work on the principle that due to the vibrations there will be a displacement of the mass, seismic mass, and this displacement of the seismic mass is going to be measured by the displacement transducer, and vibrations are measured by measuring the amplitude or the displacement. With the help of displacement, velocity, acceleration and frequency can be measured. So in this video, we studied about the measurement of vibrations. We saw that measurement, that what is vibration, what is the nature of vibrations, how the vibration can be measured by measuring the velocity, acceleration and the displacement. Then we saw the seismic transducers or seismic accelerometers, and after that we saw the different types of accelerometers along with their advantages, disadvantages and applications. So I hope that this topic is now clear to you. Thank you.